A language model has no memory of its own. At each step, everything it knows, its instructions, its history, its knowledge of your project, arrives as one sequence of tokens, the context. What it does not read, it does not know. This video is about the primary lever an agent builder has, deliberately constructing what enters the context window, from the wording of a single instruction to the shaping of a whole environment. This assumes you have a working rig and an agent with access to your files. Some of the notions discussed in this video include the model as a function of its context, the window and where attention goes, writing instructions that work, the anatomy of a well-built context, strategies past the window, automation so the rig assembles its own context, and the far edge, staging a corpus for the agent to draw from. Start with the cleanest way to see the model. Call the set of tokens it reads and emits its vocabulary. The model is a function. It takes a finite token sequence, the context, and returns a probability distribution over possible actions, tool calls, and text responses. The context determines that distribution completely. Two identical contexts induce exactly the same distribution over next actions. The realized sample is a separate matter. The temperature parameter shapes how the distribution is sampled. Near zero, the model picks the most likely action every time, which is what most agentic work wants. Higher temperatures flatten the distribution and produce more varied output, which is what you want when the goal is diverse candidates. The practical consequence is a debugging rule worth keeping. If the agent behaves unexpectedly, look first to the context. Either something unexpected is present or something necessary is absent. Now the window itself, the finite sequence the model receives at a single invocation. Frontier windows run from roughly 100,000 to 1,000,000 tokens. A dense paper is perhaps 10,000 tokens. A book, a few 100,000. A large code base exceeds any window, and these figures are a point on a fast trajectory, not a ceiling. The lesson that survives each increase: reason about how to use a window, rather than assume the next one makes the question moot. Because even inside the window, not all positions are equal. Content near the beginning is used reliably, that is primacy. Content near the end is used reliably, that is recency. And relevant information buried in the center of a long context is systematically underused, the lost in the middle effect. The curve of effective use is a valley. The practical rule follows from the shape of the curve. Place load-bearing information near the edges of the window or point to it explicitly in the instruction, rather than trusting the model to find it in the middle. Why does a bigger window not simply solve this? A useful heuristic pictures a finite attention budget. Attention weighs every token against every other, so as tokens are added, the same budget is spread more thinly, and recall of any single fact tends to fall. The effect has a name: context rot. Treat the heuristic as a heuristic. Attention is computed per head and per layer, and a model can learn to concentrate it sharply. What is exact is the architectural cost. Compute and memory grow quadratically with length. What is empirical is the behavioral cost. Longer contexts can distract the model and reduce effective retrieval. Keep the takeaway. Capacity and effective working memory are not the same thing. Adding raw capacity does not buy proportional recall, which is why selection and placement stay consequential at every window size. Prompt engineering is the practice of writing instructions that reliably elicit the behavior you want. It is best understood as specification. The prompt specifies what the model should do, the way source code specifies what a program should do, and clarity matters for the same reasons. Its place in the workflow has shifted. Most single-message instructions are now composed by the agent and by the platform beneath it. What a researcher keeps is the competence to specify and to judge what the agent produces. 5 principles account for most of the variance. Be specific about the task. Every ambiguity is a degree of freedom the model fills in on its own. Specify the output format exactly: named fields, a function signature, a fixed structure. Provide worked examples, showing correct output is more reliable than describing it. State constraints as direct prohibitions, rather than hoping the model infers them. And decompose complex tasks. A sequence of single-step instructions is more reliable than one instruction that asks for many steps. One principle deserves its own treatment. On tasks that require several reasoning steps, prompting the model to work through the task before committing to an answer can substantially improve accuracy because the final answer is conditioned on intermediate conclusions. The current form of the principle: allocate reasoning effort where the task benefits and ask for concise, checkable evidence, a short derivation, the values used, the alternative rejected, evidence rather than reasoning for its own sake. Two cautions keep this honest. Modern reasoning models often perform the work internally and expose only a summary or nothing, and even when a trace is shown, it is not a faithful audit log of how the answer was reached. The remedy is a stance used throughout this video sequence. Judge the answer against an external check, not against the plausibility of the reasoning presented beside it. Zoom out from one instruction to the whole window. A well-engineered context has a layered structure. At the base, the system prompt, the invariant instructions defining role, tools, and conventions. In practice, you rarely write it as raw text. It is realized by the project's instruction files, loaded automatically when a session starts. Above it, the task description, what to accomplish today. Then injected context, the files, snippets, and results the agent needs for this particular task. This layer changes with the task. And at the top, conversation history, prior observations and actions, growing as the session proceeds, and needing management so it does not fill the window with the irrelevant. A common failure mode is treating the system prompt as the only lever. Hours spent perfecting instructions cannot compensate for an empty injected context layer. The agent fails not because it misunderstands, but because it was never given the specific information it needed. What belongs in the injected layer? Not everything relevant. Filling the window with loosely related material degrades performance as reliably as providing too little. The right question is not what is relevant to the project, but what the agent needs to know right now to take the next action correctly. The principle: inject the minimum context required for the current step. Fitting a model: the data schema and the harness interface, not the entire code base. Proposing candidates: the domain notes and the current best result, not the fitting code. Two failure modes bracket the practice. Overconstraint: rules so exhaustive the agent cannot handle a legitimate edge case. And underspecification: instructions so vague that behavior is left to chance. Before trusting a context design, check 4 properties. Complete: it covers the scenarios that matter. Clear: each instruction is unambiguous. Consistent: the parts do not contradict. And testable: the resulting behavior can be verified. When the necessary context exceeds the window, 3 strategies extend your reach. Retrieval: index a large corpus and pull in only the most relevant pieces for the task at hand. It is a genuine trade-off, not a settled default. When a question needs evidence synthesized across a whole document, loading the full text can beat retrieving fragments. Retrieval wins when the relevant knowledge is a small, locatable slice of something far larger than any window. Summarization: compress long documents or histories into compact summaries before injection. The summary trades recall for brevity, and its quality decides how much survives. And reference, not inclusion. Give the agent a pointer to a file and the ability to open it rather than injecting the contents. This works when the agent can selectively open only the sections it needs. So far, you decide what enters the window. Automation moves that work into the rig itself, so that when the agent opens a project, it already knows what it is working on. Hooks are scripts that run on trigger events. At session start, before a tool call, after a file changes. A session start hook can summarize recent changes and load the latest results before you type a word. The instruction files are automation too, loaded at every session start. They carry the project's conventions, the key file locations, the one command run. The model context protocol standardizes the mechanism. A server exposes tools and resources through a typed interface, written once, usable by every client that speaks the protocol. Its convenience carries a context cost, and the mitigation is progressive disclosure. Expose cheap metadata first and load a full definition only when the task calls for it. Finally, prompt caching. Much of the context is stable across calls, and the cache reuses an unchanged prefix. So arrange the window from most stable to most volatile. system prompt and tools first, then corpus and examples, and only then what changes on every call. Kept identical, the shared prefix is paid for once. Everything so far pre-populates a context you still design. The far edge goes further. A trusted agent, working inside the project, assembles the context itself. The lever moves from choosing what enters the window to shaping the environment the agent builds the window from. This changes the economics. Engineering context by hand, you can bring in only what you have already studied and chosen. You are the bottleneck. Stage a corpus instead, 10 or 100 times more than any window holds, and let the agent pull in the fraction each task needs. The principle: when you engineer the context yourself, provision the window. When you empower an agent you trust, provision the corpus. What makes a corpus conducive is ordinary structure. Legible, plain text and source, not opaque formats, so standard tools work on it directly. Cataloged, one index file the agent consults first, and synopsis fronted, a cheap summary before every full source, so the agent surveys the whole library for a few tokens. The capability this buys is reverse search, from a question to the sources that bear on it. The agent works the way a researcher would. Search for the terms, scan the synopses, follow the trail, and open a few in full, every step exact and inspectable. For problems where precision or a legible trail matters, this is a first-class alternative to approximate similarity search. The premise of the whole move is trust, an agent whose reach you have bounded and whose selections you can still check. Staging 100 times more material pays off only then. Does any of this help? Measure it, the same as any engineering choice. Ablation: remove one element of the context, a document, an example, a section of the system prompt, and check whether performance on a held-out task set changes. If nothing changes, it was not contributing. Prompt sensitivity: run the same task under small variations of the instruction. High variance in the output means the instruction is underspecified. And the deciding measure: does the change improve the score on your evaluation harness? A better context beats a worse one there, or it does not. The harness decides. The chapter on one card, the model, a function of its context. The window, large, unevenly used, so place at the edges. Instructions: specify and judge. The stack, 4 layers, injected minimally. Reach: retrieve, summarize, or reference. And the far edge: provision the corpus and let a trusted agent build the window. The key idea to carry away: the context is the primary lever. Engineer it deliberately, from the wording of one instruction to the shape of the whole environment, and measure the difference it makes.